Hello everyone. Today our team will present benchmarking sentiment analysis models, where we systematically compare classical deep learning, transformer architectures, and generative large language models on the same tweet dataset. We will cover research purpose, our methods, results, and final analysis. Sentiment analysis powers applications in finance, marketing, and public opinion monitoring. Models have evolved from CNNs and LSTMs to transformers and now generative AIMs. Our goal is to benchmark these approaches head-to-head on the same dataset. We use the cargo tweet sentiment extraction dataset, 27,481 training, and 3,534 test samples. Neighbors are distributed roughly 40.5% neutral, 31.2% positive, and 28.3% negative. The picture is an example for dataset. This respectively shows word clouds of the most frequent words in neutral, positive, and negative tweets. Before cleaning, the raw tweets are dominated by high-frequency stop words such as I, do, and Z, which carry no sentiment information. So we pre-process the data to remove these distractions, and we apply regex to strip URLs or hashtags, normalize text to lowercase, remove stop words, and lematize each token, balancing noise reduction with sentiment retention. We compare two classical models, a CNN with embeddings, convolutional filters, size 3 and 5, global max pool and dropout, a bidirectional LSTM, hidden size 64 that contains forward or backward stats with dropout for context capture, optimizer add-on, learning rate equals 0.001 with cross entropy. The result is the LSTM achieves 70.2% accuracy versus CNN's 68.5% and years higher F1, especially on negative recall. However, it trends about 1.8 times lower per epoch. Next, we fine-tuned three transformers, BERT with MLM plus NSP, Robot A, optimized MLM, and dBERT A, decentered. Next, we fine-tuned three transformers, BERT with MLM plus NSP, Robot A, optimized MLM, and dBERT A, disentangled attention plus relative positions for sentiment classification. During fine-tuning, all three models were trained using the same set of hyperparameters. The training process involved optimizing the models for a multi-class classification objective using the following strategy. X3, batch size 64, optimizer Adam W, learning rate 1 map, steps 500, weight decay 0.01. dBERT AV3 best leads with 77% accuracy and 0.78 macro F1, outperforming BERT and Robot A, converging faster and showing more stable training noise. Finally, we sampled 100 tweets and queried ChatGPT and DeepSeek v2 chat under the same prompt. Temperature equals 0.3, max tokens equals 10 to compare generative performance. ChatGPT delivers balanced performance with 72% accuracy. DeepSeek excels in negative recall 93%, but struggles on neutral text 14% recall. Summarizing the overall accuracy of each model, which demonstrates that transformer-based architectures significantly outperform both classical deep learning and generative models on sentiment analysis tasks. In particular, DBERT A achieves the highest accuracy at 0.77, surpassing LSTM 0.7, CNN 0.69, ChatGPT 0.72, and DeepSeek 0.567. This result further confirms the critical role of self-attention mechanisms and enhanced positional encodings in capturing non-range dependencies and subtle contextual cues. Although generative models like ChatGPT offer balanced performance across sentiment classes, they still trail fine-tuned transformer models in raw classification accuracy. Moreover, given considerations of computational resources, cost, and reproducibility, this study prioritized open source, widely validated large language model versions. These findings indicate that for applications demanding high precision and robustness, especially those involving longer or more complex texts in sentiment analysis, DBERT A represents the state-of-the-art choice.